So the differentiation between with respect to time, which you are talking about. At which point? The Jacobian is defined like that. The Jacobian matrix because the transformation is only from x1, x2 and x3 to psi 1, psi 2 and psi 2. The integral, so it's just taking up this derivative of this with respect to time, the substantial derivative. So we saw that the best way to do this is to write this as d by dt differentiated over the reference configuration of the body of fluid. And so this would now become dE naught. So the Jacobian that would come in here, so the transformation is only from x1, x2 and x3 to psi 1, psi 2 and psi 3. The time is not being transformed, it is essentially being transformed by itself. Right? So the Jacobian that would come in here is the determinant of the Jacobian matrix, which is defined as that is a formula because it is integrated, you are converting an integral over v, which is actually dx1, dx2, dx3. This is now becoming d psi 1, d psi 2, d psi 3. So the transformation is only over that. The integral itself is not over time, it's only over the spatial coordinates. So the Jacobian that would be appropriate is only this matrix. It's the rule of mathematics. You cannot change that. That is how it is. That's how the Jacobian matrix comes into play. Right? So we're transforming x1, x2, and x3 to psi 1, psi 2, and psi 3. And these are the three transformations. So this is effectively x1 equal to and so on. x2 equal to x3. That is only the integral is only over the spatial domain. The integral is not over time. Right? So it's only the components with regard to the spatial coordinate transformation that would form the Jacobian here. So the question now is, now I can, you have to convince yourself that we can now take this into the integral. So this would now become df by dt times j plus f dj by dt, and then I have on top of it j dt naught. So the whole question now that we found was to calculate dj by dt, which is the derivative with respect to time of the determinant of the Jacobian matrix. So for that, we came up with a general formula for expressing the determinant of a 3 by 3 matrix. This is valid only for a 3 by 3 matrix. So the determinant of a matrix A can be written as when the repeated index summation convention is used. We will open the door, maybe somebody is waiting. So now we saw how to arrive at this intuitively. Write down the expression for the determinant of a 3 by 3 matrix. If you write, you will find that there are 6 terms. So you will see that you can, by rearranging the factors, you can write each in every term can be expressed in this form: a1i, a2j, and a3k. So if if you now, having done that, so having taken care of the first index, which is in this form, we now focus on the second index in each of the terms. You will find that for none of the terms, these are completely not there in any of the terms. You find that none of the two indices of the three indices are ever equal. You will find. So this will lead to an important property which will help you reduce the number of terms when this is written as an unrestricted sum. Is the property of epsilon ijk that is equal to 0 if any of these are satisfied. Any of the two indices among the three indices ij and k are equal to each other, then correspondingly the factor epsilon ijk that would multiply that term would be 0. When we saw, since we have now established that all I, j and k have to be different, if we look at the terms, three of the terms had a positive sign, while one term had a negative sign. Right? So, three of the terms had a negative sign. So, then we saw that the other property is that epsilon ijk equal to 1 if ijk can be got to 1, 2, 3. So we take this as the basic structure, order, natural order in an even number of interchanges of index. And then is equal to -1 if ijk can be reduced to 1, 2, 3 with an odd number of interchanges. We established that formula also. So this is what it is. So now what can you say about the determinant of the matrix J? Where we epsilon ij, that is easy to write down. So what for A1i, what would it reduce to? For J is defined like this: dx1 by d psi I. This would be dx2 by d psi j, dx3 by d psi k. Very easy to write down by inspection. Get rid of all this. Now I have to differentiate this. So you can easily see x1 is a function of psi, all the psi 1, psi 2, psi 3 and time. x2 is also, x3 is also. So this whole thing, when you write it out as a sum, it will all be functions of psi and time. Right? So that is what the determinant would end up being. So again, it's the constant factor. So that won't factor into the differentiation. So the simple dj by dt means is actually meaning that dj by dt keeping psi fixed. So that's very easy to do here because everything is a function of psi. Only something is a function of x, then I have to transform and use the chain rule and so on. So what I can do now is I see that since this is a constant, every term in this sum is a product of three factors. So I can differentiate term by term. In the repeated summation convention, if you don't disturb any of the indices, it will take care of the sum automatically. Right? So all I have to do is this is a product of three terms. So I have to differentiate the product. We know the product rule for differentiation. D by dx of f times g. F and g are functions of x is simply, or if you want, three functions. It would be df by dx times gh plus dg by dx times fh is dh by dx times fg. This is a simple product rule of differentiation. And differentiating again only with respect to one variable. Psi for all practical purposes is a constant. So this differentiation is very much like that differentiation. So if I do that, then I get epsilon ijk. First I differentiate this. Plus, again epsilon ijk. So this would be dx1 by d psi I, d by dt of plus, I'm going to get you right the third term. Very easy, right? So I'm going to just take one term and see what to do with it and obtain an important result of expression for the derivative of dj by dt and sort of infer what you will get from the other two terms. So if I now look at focus on this term is what I am focusing on. So if you now look at this derivative, x1 is a function of psi 1, psi 2, psi 3 and time. So when I differentiate some I take, I don't want to specify it, that's what appears there. So then that is also a function of but now here I have to differentiate again with respect to time, keeping the psi fixed. Okay, so something is a function of psi 1, psi 2, psi 3 and time. Now I have to differentiate it with respect to time, keeping psi 1, psi 2 and psi 3 fixed. So the first step is actually two derivatives, like a mixed partial derivative. The first I'm differentiating with respect to one of the three psi's, which is psi I. Now I have to again differentiate with respect to time, keeping psi fixed. So I can effectively use the property of equality of mixed partial derivatives to write this as d by dt. So d by dt merely means psi is kept fixed. So I can do this differentiation quite easily without making any transformation. Can be written as d by d psi I of dx1 by dt. Because if you simply regard this, the symbol that is confusing, what this means is d by dt keeping psi fixed. That's also like a regular partial derivative keeping psi fixed. Everything is a function of psi and time. No problem at all in differentiating and interchanging the order of differentiation. So we get this. So what is this now? dx1 by dt. It's the first component of the velocity. Velocity by definition is can be written by our notation as dx. So d1 is simply the first dx1 by dt is simply the first component of the velocity. So I can now write this as if you look at this, these two are involved in derivative of x with respect to psi, because this involves the derivative of v with respect to psi. I'm going to bring in a third term, a third factor, which involves the derivative of some component of x with respect to psi. So what I'm now going to do is to use the chain rule to write dv1, write it here first, dv1 by d sine I as dv1 by dxl times dxl by d sine I. There is a sum over ls implied. This is coming from the chain. So what I'm actually doing, you see why we are doing it shortly. So what I'm really doing is that I want to arrive this. There is no problem here because x is equal to function of psi and time. So v1 is also equal to function of psi and time. dv1 by dc psi I is also a function of psi 1, psi 2, psi 3 and time. So you might wonder why I want to disturb that. You will see the reason for that. What I want to do is to arrive at this derivative dv1 by d psi I through the spatial representation of v1. So what I am effectively saying is, don't consider v1 as a function of psi 1, psi 2 and psi 3 and time directly, but consider v1 as a function of x1, x2, x3 and time. Now transform x1 to x2 to psi and time, and also x3 to psi and time. Now ask what is dv1 by d psi I. So I have to use the chain. So I regard this as a function of x1, x2 and x3, which in turn are functions of psi 1, psi 2 and psi 3. And then I ask, through this transformation, what is the derivative dv1 by d psi I? So clearly, if I use the chain rule, what I am going to get, since this involves only derivative with respect to psi, this is transformed itself, that is not going to come into the picture. So what I will get here is dv1 by dx1 times dx1 by d psi 1 plus dv1 by dx2 and dx2 by d psi 1. Using the chain rule, this is what I will get. Again, if you are confused with how I go to, you have to review your understanding of the chain rule. So this is what it is, which is what I have written compactly as dv1 by dxl times dxl by d psi I. So this is very important to note that when you are choosing indices as summation indices, you have to be careful. For example, somebody can ask why L. It can be M, N or anything, but it cannot be either I or J or K for that matter. Those are already chosen as summation indices. So I cannot introduce a summation index which is required here, that is already there as one of the summation indices. This is an important rule that you have to remember. Other than that, since I have already chosen I, J and K, I have now to choose something which is not I, J and K. It can be L, M, N, O, P, whatever you want. So I have now written it like this. This would be epsilon I, J, K. Now what I want to do here, if you see the sum, if you look at this term, it has V1, which is a specific index, and also it has XL. So the summation here is over I, J and K, the epsilon. contains I, J and K only, it doesn't contain L. So now, what I can do is to simply shift this dV1 by dxl outside the sum. The sum over L is still retained. Actually, what this means, this is all four indices sum. Sum over I equal to 1 to 3. Now I can do it in whichever order I want. I can first take I equal to 1 and J equal to something, K equal to something, and sum over L equal to 1 to 3. Or I can do it in some other order also. I have to make sure I sum over all indices from 1 to 3. Right? So what I can do is simply shift the L equal to 1 to 3 to the last, and so I will have sum over L equal to 1 to 3. And then I have sum over I equal to 1 to 3, sum over J equal to 1 to 3, sum over K equal to 1 to 3. Now I can't write anything here. I'm going to write something here. I can't write anything here which involves the indices I, J or K. I can write anything else that I want. I can write something which involves L. Right? So what I am saying is, just put dV1 by dxl here, but I can't move this here. So that involves I, that is sum over I, J and K. So this would be what we have. Of course, L is here. So when L equal to 1, I get dV1 by dx1 times this whole sum over I, J and K evaluated for L equal to 1. Then I will put L equal to 2. So I will get dV1 by dx2 times this whole thing evaluated for L equal to 2. And for L equal to 3, I will get dV1 by dx3 times this whole sum evaluated for L equal to 3. Let us now look at this term. Since now I, J and K, they are repeated. So I can write this as, and L is also repeated inside. So I can write this as simply using the repeated index summation convention. I can write this as what can you say about this group of terms epsilon ijk times dxl by d psi a times dx2 by d psi j times dx3 by d psi k? What is the determinant? Determinant of which matrix? It's certainly it's expresses a determinant. That much you can see. Epsilon ijk a1I is replaced by L can be anything 1, 2 or 3, right? So we have to look at that, right? L can be 1, 2 or 3. Then dx2. So this is the only problem term. If I compare directly with this, that's the only problem term. But now let us see L is equal to 1. Let's consider the three cases. So it will depend on, it is the determinant of a matrix, but it will depend on which matrix it is. It will depend on whether L equal to 1 or 2 or 3. So let's say L equal to 1. Then what is this group of terms? Represent the determinant of which matrix? J, right? So L equal to 1, that group of terms, I'm not worried about this now. L equal to 1, what we get is the determinant of matrix J, which is simply denoted by the scalar capital J. That's very clear. Because after all, I have written it like this. So if I put L equal to 1, it has the same form as this. What happens if L is equal to 2? First tell me what matrix it would represent. Let's consider L equal to 2. Right? So if I now look at the form, the second and third rows are the same. The only difference will be now the first row, because that is what has changed, L. So this would be clearly dx2 by d psi 1, dx2 by d psi 2. This would be dx3, and so on. What would be the first row when L is equal to 2? You can easily guess that this would be dx2 again by d psi 1. Determinant, I have to consider the determinant. What is the value of this determinant? 0, because we know that in any matrix, square matrix for which only determinant is defined, any of the two rows or two columns are the same, then the determinant of that matrix should vanish. So L equal to 2, the value of this whole thing will be 0. You can then easily infer that from L equal to 3 also the value of epsilon I taken dx3 by d psi I will be 0, because in that case this would take place by the third row. Because first case the first two rows will be identical, second case the first and third rows would be identical. So L equal to 3 also this would be 0. So now what would this be? Dx d1 by d. So for L equal to 2 and L equal to 3, this term will be there, but it will be multiplied by 0. So finally what I am getting is dv1 by dx1 times j. So we have done all of these manipulations just for this first term. This is a sum. Now you can easily prove, and I will leave it as a good exercise for you to try it out, even though it looks quite obvious. The second term, so this is the first term, is j times dv1 by dx1. And the second sum here can be easily shown to be j times dv2 by dx2. The third term, set of terms which I haven't even written, can be shown to be 2. So I now combine this result and erase all of these derivations which are now not needed. So I can write the formula itself as dj by dt is j times dv1 by dx1 plus now we will introduce a new vector operation. This will now be a vector operator acting on a vector to give a scalar. That's called the divergence of a vector v. The divergence of any vector is a scalar. We will introduce two operators. One is very familiar to all of you, must have been the scalar product of two vectors, which will give a scalar. Right? A dot b a1 b1 to b2 b2 plus a3 b3. We also introduce a gradient of a scalar, which will give rise to a vector. That is d phi 1 by dx1 times e1 and so on. So this is the divergence. It's usually written by the gradient operator dotted with the vector, and this will be given by dA1 by dx1. I can very compactly write it as dAi by dxi, even more compactly as ai comma I, using all the notation that we have introduced. So clearly, then this very important formula probably can be attributed to Euler, very ancient formula. Because actually derivation is useful because you get to know how these determinants are expressed and how the indices work and so on. In that sense, important, but it's not so much important to remember or reproduce the proof, but the result itself is very important. Because this is the one quantity that we needed, and now we're going to go here and substitute as
J addition.
A is already here.
Already?
Oh, that's not now. Okay, so I'm just looking where there is an extra J because actually this is fine, dB naught. So I'm not taking it inside. So I just consider it only in my mind. So all of these seem to be quite clear. So J and F together are differentiated. So J would be here. So now if you see, this integral is actually, I said it's an integral over d psi 1, d psi 2, d psi 3, but I have actually introduced the quantity, the divergence of the velocity vector field, which directly is expressed in terms of the spatial coordinate. So obviously, if I have to carry out this integration, this transformation has to be employed to convert that quantity to psi and time. That's implicit. So you have to be careful in interpreting the meaning because f initially was a function anywhere of x and t. So I use the transformation and convert this. J naturally is a function of psi and t. And so here again f is considered expressed as a function of psi and time. But the divergence is expressed naturally in the spatial coordinates. But we understand that it has to be converted to a function psi and time to evaluate this integral, but that's actually not what we are going to do. What I will now do is take the G out and actually convert it back to the spatial. Because I initially had dB and I converted dB to J dB naught. So now I can go back to the x, transform back from psi to x, and then write this as integral over V, over the spatial domain that is occupied by the body of fluid at time t. And I can write this as, now I will now use the derivative, the formula for the substantial derivative to further convert it to the spatial, because everything now I want in terms of the spatial coordinates. Right? So df by dt, we already know is df by dt, spatial derivative plus v dotted with. That's what I am going to write. So that would be df by dt, which now understood that I'm writing back in terms of the spatial coordinates, plus v is also assumed to be written in terms of the spatial coordinates, even though by direct definition it's expressed in terms of the material coordinates. So, of course, the gradient of f is automatically expressed in terms of the spatial coordinates. No need for transformation. That is what I get, plus f times dB. So the j dB naught is converted back to dB. Everything is now expressed in terms of, so this actually is coming by going back to, that is where the invertibility of the two transformations come into play. So I can, so any time I want, I can move from one coordinate to other without worrying about the invertibility condition. So psi now gets transformed back to x and t. So the integral gets back to dv, which is the domain in space occupied by this body of fluid at time t. Everything now is assumed to be expressed in terms of spatial coordinates. If you are not naturally expressed, then you have to convert it to spatial coordinates. So this now is back to, because the original quantity was the integral of some quantity over the domain occupied by the fluid at time t. And I have to take the substantial derivative. So to carry out it properly, because the domain is changing with time, so that now I have to follow the body of fluid, regard the collection of fluid at time t within the volume V as the body of fluid, and I have to follow it in motion, which is what this derivative implies. I found it convenient to map back to the reference configuration. And now I am back to what I want, which is an integral over the spatial region occupied by the fluid at time t. So let us now further, this can be further simplified and written as, I'm going to prove it now. It's very easy to prove that this group of quantities be dotted with the gradient of f. So this is a vector dot product with another vector. This is a scalar. This is a scalar multiplied by another scalar. It can be shown that this can be written as the divergence of f times v. Very easy to prove. We'll prove that later. What we have now is this important final formula, which can be written as df by dt plus so I can further write this as integral v formula, and this can be regarded as the analog of this formula. This is a formula of a scalar function. What is the relation between the substantial derivative of the scalar function and the spatial derivative of the scalar function? It is a function of x and t or psi and t. Both representations are involved. And this additional term, so we see that the substantial derivative of the scalar function is spatial derivative plus some additional quantity, which is the dot product of velocity vector with the gradient of that scalar function. Now, if I want to consider the integral of a scalar function, then you can ask what is the relationship between the substantial derivative of that integral and the spatial derivative of that integral. Clearly, substantial derivative again is equal to the spatial derivative of that integral plus this integral of the divergence of f times v. This is entirely analogous to this formula and quite easy to remember, but this is probably something that you should remember. This maybe is not quite needed because there are so many other forms in which we are going to express this expression. Are there any questions? So now another way of writing this, still another way of writing this is now converted to an area integral rather than a volume integral. So this is what will be provided by the divergence theorem. I will explain that in detail in the next class. So this can be written as the dot product of f times v, which is the quantity that is appearing within the divergence, times the unit normal, unit outward normal of what is this a and what is the integration over. So I started out by saying consider a time t where and a region occupied by the fluid, we will call this the volume region occupied by the fluid. And you are considering the quantity which is the integration of some f, scale function f over this volume. And I want the substantial derivative. That is equal to spatial derivative. It can either be written as a volume integral, that additional term, or it can be written as an area integral using the so-called divergence theorem. Now, the meaning of this is that this A is this surface bounding the region of fluid occupied by the fluid at time t. So the n is the unit normal vector at every point on the area. It is going to change. So the orientation of the surface is changing to n prime, n double prime, and so on. So I have to calculate the dot product at every point of this and integrate it over the surface. So we are converting a volume integral into a surface integral or an area integral. So this is the area over which I have to integrate. Now what is the use of this? It has some good physical, a nice physical interpretation which we will discuss in the next class. So the remaining 2 minutes of time, I want to discuss something away from the divergence and gradient. There is an option of converting the 8 a.m. lecture on Monday to an extended lecture on Tuesday, if it is acceptable to all of you. It's only an option. I'm proposing 12 to instead of 1, we can have it until 1:30, an extended lecture. So it will help avoid the problems that students need to have at the 8 o'clock class. So how many of you have an objection to this? Is there anyone who has you have an objection? What is the objection?